Going live. Hey everybody, I think we're live. Welcome to Game Engine's class on Thursday morning. So today's class is going to be all about the A-star algorithm. And yeah, what have I got for you guys? Right, so if you've ever used the nav mesh in Unity or the nav mesh agent in Unity, then you'll be familiar with the idea of calculating the lowest cost path in a scene, like between two, like start location and end location. And pretty much every video game like invented or made, you know, where you have to move characters around in maybe the last 20 years will use this algorithm in addition to things like Google Maps and GPS. Basically, this algorithm is all about, like I say, calculating the lowest cost path between two nodes on a graph, and it has lots of applications in video games and, like I say, in GPS and pathfinding and mapping and stuff as well. And it's a really interesting algorithm, and there's lots of interesting aspects to it. Number one is like the whole conception of the algorithm is really cool, and then also from a computer science perspective, there are some very interesting learning outcomes when you study A-star to do with like how you keep track of things on the open list and the closed list, and then how you do the access for the open and closed list. Basically how to make this algorithm run really quickly. I'm looking around here because there's Doggy. So we just got a new puppy. Come here, puppy. I'll introduce you to puppy. This is Lucy the puppy. So if I get distracted during the live stream, it's just because Lucy maybe is chewing on something or having a pee or something. Anyway, let's begin. I'm going to start with some PowerPoint slides just to introduce this algorithm. We'll see how far we get today. When I introduce the algorithm, we'll do kind of like a walkthrough of the algorithm for several iterations of it so you understand how it works. And then I have a really cool demo in Unity of an implementation of the A-star in C#. And we can look at basically, you know, what the code looks like when you want to implement this algorithm from scratch. So that's the crack, everybody. All right, let's begin. So, yeah. Let me get my PowerPoint up here. Let me just hit F5 on it. Let me run the PowerPoint and see what happens. View, slideshow, from beginning. I just said, no, I don't want to do that. Duplicate slideshow, swap presenter slide. I just want the slides in one window and everything else in another window. I wonder if this is even going to work. There's the OBS thing there. Let me see if I get the YouTube chat going in the other window. Alright, I think we're probably alright. Oh, hang on, I need to do OBS because I need to flip over and show the slides. Here we go. Alright, I think the slides are going. Let me know in the chat if you can see the slides okay when they start. Yeah, still becoming familiar with all of this different technology for YouTube. Anyway, so pathfinding with A-star. Let's begin. Alrighty. Okay. So what are we going to learn in this class? We're going to learn what are navigation, what are graphs, what is a graph, what is it used for in video games, why is it useful to know a little bit about graph theory, and computer science students will be familiar with graphs and graph theory because it's a part of any algorithms course on a computer science degree. How to create navigation graphs, and then we look at how to calculate the lowest cost path between two nodes on a graph using A-star algorithm. And what does that even mean? Lowest cost path. What does the lowest cost path mean? And then we look at how to implement A-star in C#, and we're going to focus specifically on like what data structures you use to hold the open and closed lists. So computer games is necessary for characters to make decisions. You know, you might say to a character, you're in one room, go and find your way into this other room, and then the character has to go and calculate a path that brings it from one part of the scene to another part of the scene, and then it's going to follow the path. So this is relatively easy for people, but like it does require you to know the area that you're traveling through, and also to have some concept of what does it mean to like get from one part to another with the lowest cost. Right, so here's an example from an RTS game, very familiar, and it's really easy to see A-star from RTS games because you can select a unit and you can then click another part of the world, and then the unit is able to find its way to the other part of the world. So, and it does that, like sometimes you look even in, this is an old RTS game, this is like Command and Conquer Generals, but sometimes you'll see, oh, why is it going that way? And then you look at it and you realize, oh, okay, that is actually a very good path. So yeah, this sometimes might involve going over mountains, right? So this is the whole point about lowest cost. Um, Lowest cost doesn't necessarily mean the shortest path, because the shortest path could mean that you have to go over a mountain, and then maybe you want to assign a cost to traveling up the mountain versus going down the mountain. Down the mountain might have a lower cost than going up the mountain, so you want to avoid mountains. You might have to cross a bridge. You might have a cost associated with crossing a bridge, or swimming across water might have a higher cost than walking on a road, for example. It might mean climbing ladders, might mean opening a door, and then maybe the door is going to close behind you and you can't go back. So is that another thing that needs to be taken into consideration? And all of these problems can be solved by using this algorithm called the A-star algorithm. So first of all, a little introduction. The A-star algorithm is what's called a graph traversal algorithm. So what is a graph? A graph basically is the set of nodes and edges, right? So nodes in this diagram are represented by the little blue circles, and then the edges connect up the nodes. And the edges can be directed or undirected. In other words, you might be able to travel from this node to this node, but not back again from this node here. Again, this could be an example of if these were locations on a map. And this could be somewhere, maybe where if you go across this bridge here, the bridge collapses underneath you. So you can go in one direction in this graph, but you can't go in both directions. Or maybe a door closes. So, yeah, that's what a graph. Graphs are used all over the place in computer science. They're used a lot in state space searches, technology trees, dependency graphs. These are things that you might use a graph, or you might have come across graphs in games before, like tech trees, for example. State graphs. Let's skip on. Like this is civilization, right? So civilization, you have a tech tree, and you gotta build this thing, and then you research this thing, and then you build this thing, and you get this amount of money, and it enables you to produce this further thing down the line. So that's an example of a graph, where each node in the graph is like a thing that can be achieved, and then you have ways of transitioning from one node to the next, which is by maybe researching a technology or getting some resource or whatever. So these are the first two algorithms here are classic computer science algorithms for traversing a graph. So graphs, by the way, I was talking about state graphs and stuff. I'm talking about tech trees. Graphs, of course, can be used for navigation as well, where you have nodes being locations on a map and edges being ways of getting from one location to another location. But anyway, in order to traverse the graph or search through the graph, there's lots of different algorithms you can use. You can use a depth-first search algorithm. And a depth-first search means basically these algorithms, what distinguishes them is which nodes on the graph you search next. And with a depth-first search, you start at one root node, and then you expand one of its child nodes, one of the nodes connected to it, and then you're going to expand one of its child nodes, and so on down until you reach what's called a leaf. Or with a breadth-first search, you expand all the adjacent nodes, or all the nodes that are connected to a node, and then you kind of expand outwards from each one of those, and so on. And then you have Dijkstra's algorithm, which is the lowest cost path. And then A-star algorithm is also lowest cost path to a destination, but A-star is a directed, it uses this extra thing called a heuristic, which we'll get to. So that's graph traversal. I actually think I have got some cool programs which, after the PowerPoint, just to show you what these things look like, maybe. See if I can find them. These are just implementations in C++. So A-star graph traversal algorithm allows you to find the lowest cost path through a graph, which is not always the same as the shortest path or a path with fused nodes. Hey, here's just a quote from Edvard Dijkstra. He was the guy who invented Dijkstra's shortest path algorithm. And this is a really cool quote. The question of whether computers can think is rather like a question of whether a submarine can swim. I really like that quote. So here we go. Yeah, so we're going to make, in today's example, we're going to make a navigation graph as opposed to a tech tree or a state space search or whatever. And yeah, this is also known as a Euclidean graph. And then these graphs can be constructed from other algorithms. Simple algorithms like just traversing across the, if it's a 2D graph, it'll be just node by node, placing a node at intervals. So you got basically a tile-based graph. You could also use a flood fill algorithm, which basically takes a point and expands outwards. or most video games use an algorithm called triangulation, which I'll show you to make the navigation graph. Some of this is not that relevant. These are old slides. Yeah, there's loads of ways you can represent graphs. You can use an adjacency matrix or an adjacency list, computer science stuff. Flood fill algorithm: start at one node, expand outwards, and place a node basically at intervals. XY traversal, the same kind of thing. Triangulation. Yeah, this is how Unity works. This is how Unity generates navigation graphs. Basically, all the geometry is expanded outwards and nodes are placed around, and then you're kind of doing some raycasting thing to check to see are the nodes navigable from one to another, and then that's basically triangulation. Alright, here we go. The A-star algorithm. The A-star algorithm. Hey, I wanted to also just say, maybe I'll finish the PowerPoint slides because I want to take note of two things. First of all, a great paper I want you guys reference. It's why I say it's a great paper, because I wrote it. Yeah, it's a paper that I wrote in 2006 and it got published at the Sea Games conference in Louisville in Kentucky, all about the A-star algorithm and how you implement the A-star algorithm in C++. And also it has pseudocode and a great description about things like the open and close list. So I'll link to that paper, right? I'll give you the reference for that. So this is how the A-star algorithm works. So this is like this diagram you see here on the left, right? This is a simplified, you know, like imagine this is basically the world that we want to navigate. And in this example here, the world is divided up into tiles. All right, so each tile is a node in a graph, and in this navigation graph, we assume that you can traverse from one node to all the adjacent nodes. So basically, every single node has got like 1, 2, 3, 4, 5, 6, 7, 8 adjacent nodes, and like from the green node here, for example, you can travel to any of these adjacent squares here. These blue things, this blue thing here in the middle is a wall, and this red thing here is basically the destination. So I want this green guy basically to get to this red guy, and I want to get it to, you know, the most efficient way. You can see that there's like you know, there's lots of possible solutions. If you're using depth first search or breadth first search, you would get a path from the green one to the red one, but it might not. It would definitely not be an optimal path. Anyway. So here we go. This is basically the setup for the A-star algorithm. So we have all of these squares representing nodes. They can all be traversed via an edge which joins every node to every adjacent node. Cool! How does the A-star algorithm work? Okay, the general approach is we start at the starting point, checking all the adjacent squares, and then search outwards until we find our target. Here we go. So there's one thing. Oh yeah, well actually I'm probably going to get to it in a little bit, right? So how does it work? Okay, so from the green square, oh yeah, this algorithm keeps track of two lists. These are called the open list and the closed list. So the open list is nodes on the graph that we still potentially want to look at, and the closed list is nodes on the graph that we're finished looking at, right? So yeah, the algorithm basically continues until you start at the start node, expanding outwards, and will continue until the end node on the graph is found. So here we go. Add A to the open list of squares to be considered. Right. So first thing, the algorithm starts, and the green square gets added to the open list, and then you go into a while loop that basically says while you haven't found the destination node, keep on running. So the first thing that happens then is that node gets popped off the open list, and all its adjacent nodes are put onto the open list. So, and then you also remember, like, how did you get to that adjacent node? So you basically store like the direction from the start node, or the path from the start node to the adjacent node. Okay. And then the A is dropped and it gets added to the closed list of squares. So you don't need to look at it anymore. And then so that's the first iteration of the A-star algorithm. And then you choose one of the adjacent squares on the open list, repeat the earlier process, and keep on going until you reach the destination node. So here's like one aspect. That's the sort of like core of the A-star algorithm. So now there's the next question, like which node do you expand next? And the answer to this is you expand the node with the lowest F score. And what does the F score mean? For every node that you expand, you calculate three numbers, right? These are called the F, G, and H numbers. And the pseudocode basically is that F equals G plus H for every node. Right, so what's G? G is the movement cost to move from the starting point. Let's see, the movement cost to move from the starting point A to following the path generated to get there. So G is basically the cost from the start node to the current node. The start node to like the parent node plus the parent node to the node that I'm going to add on the list. I'll say that again, right? So the G score is the cost of getting from the start to the parent plus the parent to the node that I want to add on the open list, to the open list, all right? The H score is the heuristic cost from the node that I want to add to the destination. So what is a heuristic? A heuristic is what's called a rule of thumb. So it's an estimated cost. Like it's how, you know, it's an estimate of like what is the cost of getting from the node I want to add to the destination node. And then the F score is equal to the G plus H. So everything gets added to the open list, and every iteration of the algorithm, the node that you take off is the node with the lowest F score. All of this, like, bear with me for a little bit, because I'm going to do like a worked example of this, and you'll see how all this stuff works, and then we'll look at the C# code. You see it's not that complicated. So calculating the H score, right? The H score is the heuristic cost. So the H score, like there's loads of different ways to calculate it, but you know, we will use one actually called the Manhattan distance. So that Manhattan distance is like basically, you know, I got to show you a diagram, I think, right? Here we go. I'll show you in the diagram. Okay, here we go. And I'll show you how these F, G, and H scores are calculated. And then, yeah, you'll see then like what I mean by the heuristic and the cost function and all of that stuff. All right, so here we go. Right, this is iterating through the A* algorithm here. Let me see. Is this the best way to do it? Because I actually have no, I think this is fine. All right, cool. So we say right the green square there. The green square gets pushed onto the open list. And then you go into this while loop where you're basically going to pop the one with the lowest F score off the open list and then expand all the adjacent nodes. So that's basically what's happening here in the algorithm. So, yeah. So the first node that gets popped off is the green one. And then these are the F, G, and H scores printed like for each of the adjacent nodes. So let's look at the, this node here is the G score here in the bottom left-hand corner. All right. So for this little simplified example here, I'm assigning a cost of 10 to horizontal and vertical movement and a cost of 14 for diagonal movement. So hopefully that makes sense for you guys, right? If you think of like a right angle triangle, you know, the two sides of a right angle triangle, if they're of length 1, then the hypotenuse of that right angle triangle is going to be of length the square root of 2, which is basically 1.4. So all I'm doing here is I'm just making everything into integers, right? So I'm saying a cost of moving horizontally is going to be 10, you know, and a cost of moving diagonally is going to be like the square root of 200, if you want to think of it like that, which is roughly 14. No, not, it's 10 squared, square root of 200. Okay, I think I'm right there. Yeah, I think it's 14, roughly 14, not exactly 14. Somebody can check in the chat. Anyway, so these are the G scores. So we got 10, got 14, got 10, got 14, got 10, 14. This number here in the bottom right hand corner, this is the H score. So the H score is the heuristic score, and in this example here, we're using what's called the Manhattan distance heuristic. And the Manhattan distance heuristic is basically what you do is you count the number of squares this way and the number of squares this way that you need to get from here to the destination. It's called the Manhattan distance because, like, if you think of how Manhattan is laid out into sort of a grid pattern, so this basically divides, says like it's, it's the grid on the horizontal and the vertical, like, thing, right? So anyway, here we go. Look at this, 40. So why is it 40? Look, this is 10, 20, 30, 40. This one here is 30. 10, 20, 30. This one here is 40. 10, 20, 30, 40. This is 50 because it's like 10, 20, 30, 40, and 50. 60, 10, 20, 30, 40, 50, 60. So there you go. That's how those H scores are calculated. And then this here is the F, and the F is equal to the G plus H. The G being the cost of getting from the start to my parent and my parent to me. That's basically what the G score is. So the start is 0. To get from the start to the start is 0, and then to get from the start to this one is going to be a cost of 14. To get from the start to here is going to be a cost of 14, and from here is a cost of 14. I'm thinking we probably should have looked at the pseudocode for this before we jumped into this example, but maybe you just take a quick look at it. I think because we're in the middle of the PowerPoint, I'll keep going here, right? So that's basically the first iteration of the A-star algorithm. Calculated the F, G, and H scores. Now we have this next question is, what is the node that, where do we go from here? How do you find out what's the next node that we look at? And the next node we're going to look at is going to be the node with the lowest F score. So looking at this here, there's two nodes with a low F score. This is one here, this one has got the lowest F score. So this is the node I'm going to expand next, right? So let's see what happens. Continuing the search, choose the lowest F score square from the ones on the open list. Let me do something here. Let me do this thing here. That's screen dot. Video capture. We're on screen 1 here. USB camera. Yeah, it's supposed to be showing my camera, but it isn't actually coming up here. Never mind. Video capture device. If I remove it and add it again, am I sure I want to do that? Display capture, video capture. No. I wonder why that is. Okay, never mind. Okay, so we choose the one with the lowest F score. Okay, here's basically what happens next. We choose the one with the lowest F score, drop it from the open list, add it to the closed list, and then we check all the adjacent squares. Oh yeah, ignoring those that are already on the closed list or unwalkable, add squares to the open list if you're not on the open list already. Make the selected square the parent of the new squares. If the adjacent square is already on the open list, you check if you get a lower cost path to that square. So you basically recalculate the F, G, and H scores for that node. And when you recalculate the F, G, and H scores, if you get a lower G score, then you update that node's parent. That's the A star. There we go, right? So anyway, this is the first iteration of it. First iteration of it is all of these ones with little green squares around them are now on the open list. And then the next node that gets expanded is this one here, the one with the node, the one with the value of 40. So then for that, what's going to happen here? All of the adjacent nodes are their F, G, and H scores are recalculated, and if we find a lower cost to go this direction to one of the adjacent nodes, then its parent is updated and the scores are calculated. But in this case, I don't think it's going to happen. So what's going to happen is just the algorithm is going to proceed to choose one of the ones at the top or the bottom, which is the ones with the scores of 54, and that's what happened. So this time it took the one with 54, and now it's like expanding outwards and calculating the F, G, and H scores of 74 and 88. And there's 54 up at the top. So the one at the top is the one here. This is the next one that's going to get expanded. So that one gets expanded. And on, I think maybe I've skipped through a couple of steps here, but on until we reach the destination. Once you reach the destination, the algorithm backtracks. So it basically goes parent to parent, parent to parent, back from the destination to the start and up and basically builds the path like that. So that's how it works. Hey, I have an actual a couple of good demos here to show you guys, which will hopefully make this a little bit more clear. Let's have a look at this. These are the Buckland executables here. These are from Matt Buckland's Programming Game AI by Example book. Yeah, my webcam doesn't seem to want to get picked up right now. That's okay. Alrighty. Pathfinder. Chapter 8. I'm looking for the graphs one. No. Pathfinder. Damn, maybe I don't have these ones. Oh yeah, I do have it. Pathfinder. Excellent. Here we go. So, here's just a little example, okay? So, in this example here, the green one is the start. This is from Matt Buckland's Programming Game AI example. The red one is the destination. And then we can draw in some walls like this. This is going to be, I think, like a higher cost to travel over. And then this is water. So here's basically the navigation graph here. And now I think we can do, yeah, a couple of examples. Depth first search, breadth first search, Dijkstra's shortest path algorithm, and A-star. This is depth first search. So depth first search graph traversal algorithm, basically, yeah, we're going to go expand one node and then expand its child and expand its child and keep on going, expanding down child nodes of child nodes until eventually you reach the destination node, and that's the path that the depth first search algorithm will give you. Breadth first search gives you this algorithm here, so basically, or this type of structure, so you're going to expand outwards and keep on expanding outwards until you reach the destination node. Dijkstra's shortest path algorithm gives you the lowest cost path, but it has to expand like lots of additional nodes. A-star gives you this sort of thing here. So because it uses this heuristic, it is a very efficient way of calculating the lowest cost graph. That's, you know, just wanted to show you that one. Let me see if I can get the Blitz Basic one working, because then we can see those numbers getting calculated. The A-star Pathfinder, the Blitz Basic version. Oh, not this one. The Visual C++ version. So the basics, A-star basics. So I need to switch over onto the other screen. There we go. I think this is it. And then if I switch over, bring this thing over here, and then we take a look at this guy here. I think okay, let's do this. A-star basics. This is quite an old program, so it's just a bit tricky to get it running on the live stream. So I'll leave that over there. I'm going to come back over to this thing. Probably need to restart it. Okay, I think it's going to be alright now. Alright, it doesn't even run like a 1080, so it might just appear as a sort of a window up on the top there. And if I actually Alt-Tab over to that thing, it actually stops drawing. So I think I probably just need to stick onto the Blitz Basic thing here. Okay, cool. Hopefully it will draw. Okay, let's do this one more time, and then I think I'll just step through this thing. Okay, cool. So I know this is probably appearing in the top left hand corner, a bit of a technical thing. I don't really know how to fix that. So anyway, we'll just proceed. So, right, this green square here is where we want to start from. This red square here is where we want to move to, and we can draw in a little wall here like this. Again, every square here represents a node, and adjacent nodes represent edges. So, okay, so going back to this sort of like algorithm again, right? So again, the main sort of like core things of it are we keep track of an open list, a closed list, and we have this heuristic which decides like which nodes we expand next. All right, that's kind of like the core features or the core things of A star. So first thing that happens is that green node gets pushed onto the open list, and then you go into a while loop which basically says like while there are more nodes to be expanded, go and expand outwards. And so the first thing that happens is the green node gets pulled off the open list and its adjacent nodes are expanded. And the F, G, and H scores are calculated like that. So 14, 10, 10, 14, all those numbers, that is the G score. The G score is basically defined as the cost of getting from the start to the current node plus the current node to the start to the parent plus the parent to the node that you want to expand, the current node, adjacent node. So we've got scores of 10 and 14. 90 then there is going to be the heuristic cost. So like that's basically the straight line horizontal distance and the straight line vertical distance. So that 90 is going to be like 10, 20, 30, 40, 50, 60, 70, 80, 90. And then, you know, you can see similarly for the values of 100 and 110. They're calculated like that. And then we do one more iteration of it. And then the next node that gets expanded is that node just to the right of the 90 node. And then these nodes, you can see basically the nodes getting expanded with the lowest F score. So the algorithm has to go through a few like false paths before it actually finds nodes which are going to end up as being part of the path. And then the backtracking happens from the destination back to the start. Yeah, I was just thinking probably we should have even looked at the pseudocode for this before we started looking at the run through, but why don't we take a look at that now? This is linked to from the website for the course. Oh, here, I need to switch windows now. Oh yes, screen 2. Yeah, awesome. Yeah, so this is linked to from the website for the course. This is my kind of like paper about A star. I think I include some pseudocode. This is the pseudocode. Awesome. Okay, why didn't we start with this? I'll remember this next time I'm teaching this class. Anyway, so this is the find path pseudocode, right? Basically, we got open list and we got closed list. And we assign F, G, and H scores for the first node, which is basically the start node, to be all zeros. And then we push the start node onto the open list. And then while there are nodes on the open list, we pop off a value from the open list with the lowest F score. And then you check to see if you've reached the destination. If you've reached the destination, you jump out of the jump out of this and construct the path basically by going back through all of the parent nodes. And otherwise, you push the node that you just popped onto the closed list, and then go through every adjacent node to the node that you just popped off. And then if the adjacent node is traversable, in other words, if it's a node on the graph, this is like optional really. If it doesn't already exist on the closed list and it doesn't exist on the open list, you calculate the F, G, and H scores and then push it onto the open list. So there's the H scores, the heuristic cost, which, you know, you can see how that's calculated as like either the Manhattan distance or Euclidean distance. Manhattan distance being like straight line horizontal, straight line vertical distance. The G score is the cost of getting from the start to my parent, which is the parent's G score, plus the cost of getting to the adjacent node. So the F score then is equal to the G plus H node. The G plus H scores, and then the adjacent node's parent gets assigned to be the parent, and it gets pushed onto the open list. This little else case here is if it already exists on the open list. So this is a thing called edge relaxation that this algorithm also implements. And this is basically the case where you know, maybe there's a short, maybe you've already found this node via a different path, and now you found this node like via a different path, and it's a faster path. I kind of need to draw this to show you when this can potentially happen. But it's essentially like if you've already expanded the node, but now you've come across this node again via a different route, and it's actually a lower cost version, so you update the node's parent. So that is the pseudocode for A-star algorithm. Right, let's take a look at this in Unity to see how it kind of works. I hope like that wasn't too confusing. I probably realized I should have started with the pseudocode and then done the example afterwards. But like, hopefully you get the main features of A-star. The main features of A-star are the open and close list, the heuristic, the FG and H scores, and then this edge relaxation thing can also like sometimes occur in A-star. Alright, but it's guaranteed to give you the lowest cost path. That's the cool thing about it. Alright, let's take a look at an implementation of A-star in Unity. Cool. Alright. Let me just open up another scene here. Let me open up the avoidance scene. Alright, so this is the avoidance scene that we were working on last week. So this has basically obstacle avoidance behavior turned on for this little void here. And these little green things are red balls are obstacles for this void to like steer around on its way towards getting towards this destination here. Alright, so check it out, right? Let's check out. The void basically has obstacle avoidance and it has seek behavior turned on. So obstacle avoidance is going to avoid these things because they're on the obstacle layer. And then this is the destination where we're going to try and reach. So I'm going to hit play, see what happens. Here we go. So this guy is like happily swimming along. It sees an obstacle and it swims along, and then it's like heading towards the destination, and it perceives another obstacle, so it swims around that, and then it sees that other little thingy, and so it swims around that, and then finally it reaches its destination. Hooray! Ready. Let's open up another scene here, and this scene is in the repo. This scene is the Pathfinder scene, right? So this scene I've kind of similarly set up, right? I have a little void here, and this void basically, it's got nothing enabled at the moment. It basically has a void, and it also has the follow path behavior. It doesn't have the avoidance behavior, right? And then here's the target over here, and I've placed a few obstacles in the way. So before I enable the void on this void, I just want to show you, here is another game object here, and this game object has a script on it called Pathfinder and a script called Path. So Pathfinder is implementing the A-star algorithm. So let's just have a quick look at like how this, yeah, definitely wants to use the priority queue. So let's just have a look and see how it works first of all. Or like I'll just show you what it does, and then we'll have a look at the code. We're probably going to have to continue this in tomorrow's class because I wasn't quite sure how long this was going to take, you know. But it's quite cool. Alright. So here is the scene. Now the path is getting drawn just with a gizmo, right? And here's where the path starts. And then there's these obstacles here. And then here is the destination here, okay? So there's a few things that we can do. This path is getting calculated once per frame. If you look at the Pathfinder there, it's still taking less than a millisecond to calculate this using the A-star algorithm. You know, if we make it slightly bigger, and there's 55 nodes on the open list when it does the calculation. Anyway, there's a few things we can do here like this, because this path is getting calculated every frame, and it's fine to do that. Fine to do that for this simple example here. But look what you can do here. I can take this little sphere and I can move it around like this, and it'll recalculate the path. So it's recalculating the path, you know, using A-star. And then you can say whether you want to have 3D paths or 2D paths, whether you want to add nodes at the top or nodes on the bottom. So if you go down to Pathfinder, you can say is 3D. And that changes the shape of the graph, because sometimes it's going to generate a node which goes downwards as opposed to going upwards. So I can move these obstacles around, and you can see it will regenerate the path. Like that. So that's A-star in action, right? That's what it looks like. Oh, there's also another little thing you can do here in the Pathfinder script, which is to smooth the path. And that basically removes lots of nodes from the path that are, like, as you can see, that they're not really necessary, because this is doing the same type of navigation graph. This is using a sort of like a tile-based navigation graph in this implementation. Okay, so what else do I want to show you before we take a look at the code here? Oh yeah, I want to show you what it looks like when it runs. Let me go back into the Pathfinder code here, and this actually will crash if I put this in update, just because the Boyd is trying to follow the path, and if every frame the path is getting recalculated, the Boyd can't follow the path. So you just put this into start instead. Oh, you know what? Let me just rename that to start. I'll show you the Boyd following the path. So there's start. Let's jump back over here into Unity, and let's check the Boyd out following the path now. Right. So this is not using obstacle avoidance like the previous scene. This is just using the path that's generated in order to like navigate from here to the destination whilst avoiding obstacles. So let's check the path out. See what the Boyd looks like now. So when I hit play, maximize on play is turned on. Oh, hang on, let's turn the Boyd on. Boyd is turned on now. Hit the play button. So now this guy is following the lowest cost path. Oh, don't crash. Thank you. So there he is following the path. I can select the Boyd over here and go follow, and you can see that it is following from one waypoint to the next to get to the destination. So there we go. Boyd eventually reaches the destination. So like I say, this is using path following or path finding and path following rather than use the obstacle avoidance like you can see in the previous scene. So that's the A-star algorithm in C#. In Unity, that's what it looks like when it's running. Let's take a look at it, and you'll see that it pretty much closely matches up to the pseudocode, right? Oh, there's an interesting little twist to this version of A-star, right? A-star algorithm typically requires you to generate a navigation graph in advance, but the navigation graph is really just a concept. Okay, so this particular implementation of A-star doesn't actually pre-generate a navigation graph. What it does is it builds the navigation graph as it's expanding nodes outwards, and the algorithm basically looks to see, when it's expanding adjacent nodes, it does a raycast to see is there anything in the way and is there basically a node there. So this algorithm doesn't pre-generate the navigation graph, this implementation. But anyway, let's have a look and see what it looks like. So basically, I suppose we should probably talk about this a little bit first. There's one extra thing I wanted to kind of share with you guys, and it's basically to do with how you implement the open and closed lists. I'll tell you what, let's look at the actual code here first of all, and then maybe we'll talk about the open and closed list. Because there's a big reveal here. Because there's various ways to make this algorithm, efficient by using the right data structures. Sean asked a question in the chat. Is the cost the distance from the center of one node to the center of the node that it's targeting? Yep, that's exactly it. That's the cost. And for this implementation, I'm assigning vertical costs of, I say 10. Vertical and horizontal is 10, and diagonal it means 14. That's the cost. Yeah. Okay, cool. I think maybe I will just discuss this a little bit before we get into it. The actual implementation is very close to the pseudocode. There's an open list, there's a closed list. The algorithm here is find path, right? So So find path, basically, first of all, it rounds everything to a grid size. So yeah, this position to voxel basically is just rounding everything to the nearest like grid size. So if I'm basically saying that the grid size is 5 is the grid size, then this just rounds everything to the nearest unit of 5. That's what position to voxel does here. Open lists and the closed lists are all cleared. And then we create a node, a graph node, calculate the F, G, and H scores, and assign a position value to it, add it to the open list, and we actually enqueue it, which I'll maybe talk about this because this is quite useful and quite relevant. Yeah, here we go. And then I'm just doing some timing stuff here. But basically, while there is a node on the open list, while open.count is greater than 0, we remove something from the top of the open list. Check to see have we reached the destination. If we haven't reached the destination, we add the adjacent nodes and then remove it from the open list and add it to the closed list. So that's what's basically happening here. Open.remove is removing from the open list. Closed is adding it to the closed list. And then we go to add adjacent nodes. Let's look at add adjacent nodes. So add adjacent nodes is just doing like -1 on the x, -1 on the y, -1 on the z, up as far as 1. So it's basically finding the 8 adjacent nodes, and then this method here is add if valid. So this is basically calculating the positions of the adjacent nodes and then add if valid. So first of all, this is the is navigable test, right? Like I say, I don't pre-generate the navigation graph here. What I'm doing is I do a raycast from the center of the current node to the center of the adjacent node, and if the raycast is if the ray doesn't hit anything, I basically say that there's a node there. I'm going to go through this again in tomorrow's class, I think, because this is like there's quite a lot of useful kind of learning outcomes from this example, I think. So then I'm checking to see is it not on the closed list? Is it not on the open list? That means it's not on the open list, it's not on the closed list. We're going to create a new node, calculate the F, G, and H scores for that node, and then add it to the open list. All right, so the G score is the cost from, like I say, the parent's G score plus the cost of getting from this node to the adjacent node. The heuristic cost is like that Manhattan distance heuristic, you know, so it's basically the straight line X, straight line Y, straight line Z difference. So actually even look, I'll show you what heuristic, the method looks like. And then we're calculating the F score is equals to the G score plus the H score and then adding it to the open list. Here is an example of it's not on the open list. Sorry, if it's not on the open list, it gets added to the open list. If it's already on the open list, we recalculate the F, G, and H scores and see if the G score is lower. And if the G score is lower, then you update the node on the open list, basically to say that it has a new parent. You found like a shorter path to this node. That's essentially what's happening there. So that's basically the implementation of the A star. Let's have a look at the heuristic. The heuristic, like I say, is just the straight line distance on the X, Y, and Z. So you see it's just like the absolute value of the difference between the X's, the difference between the Y's, the difference between the Z's, and then multiplying that by 10. So let's see, what else have we got here? That's the cost. Okay, cool. That's the heuristic. Oh yeah, that's the heuristic. The cost is exactly the same. The cost is just returning like the either 10 or 14, whether it's horizontal or diagonal. Horizontal or vertical, it's going to be 10. If it's diagonal, it's going to be 14. And there's the raycast thing. It's just doing a raycast. That's how the algorithm works, everybody. Now, there's one other thing which is worth discussing here. Oh yeah, like, let's finish this. Let's finish. I'm just thinking. So we're adding the adjacent nodes, blah, blah, blah. Okay, fine, cool. So once we get out of this while loop, that means that I've popped a node off the open list, which is the destination. And if you pop it off, it's the destination. What do? You basically backtrack from the destination to the start and add all the parents, so via the parents. And that's pretty much it. That's the A-star algorithm. Now, the one thing, we only have like 6 minutes left, but this is like quite a cool thing, quite a cool topic, and I'd really like to have a whiteboard for this. I'll start a whiteboard, see how it goes. We only have 6 minutes. Maybe we'll come back to this tomorrow. I think maybe I'll mention it. I'll tell you what, I'll tee it up for you guys. We'll just mention it today, and then I think we'll come back to it in tomorrow's class because it's quite relevant. So I just want to maybe just tee this up. I just want to think about this for tomorrow. Where's my whiteboard? Here we go. Oh, here we go. Whiteboard. So we've seen the A-star algorithm in action, and we've seen what the C# code looks like, and you've probably even like had a sneak peek and you know the answer to this question already, because if you've had a look at the C# code, or you were paying attention when I flashed up the code there, you would know that there's like very important, how do you make A-star fast? How we make A-star algorithm fast is by using an optimized data structure for the two data structures that it needs. It needs the open list and it needs the closed list. Never mind about the graph, because as you can see, I'm like building the graph as I go. But we have these two lists called the open lists and the closed list, and we need to store nodes. These are going to store nodes. Or like, and every node is going to have a location and a parent. Alright, so let's just make a note of this. Node actually has three things. Oh yeah, sorry, it has the location. Actually, let's call it position. And then it also has a pointer to its parent. That's going to be like a reference, okay? So that's every node on the graph has got that thing. And so then we have this data structure which is going to hold nodes, and we have this closed data structure which is also going to hold nodes, all right? So the question then is like, what do we use to hold the open and closed data structures? We have loads of possible data structures we could use, you know, because we have tons of data structures. Like the big question I suppose is like, why, you know, let's say if we just throw down a few, could we store these in an array? Definitely. Could we store them in a list? Could we store them in some sort of dictionary or map? Could we store them in a queue? Could we store them in a stack? So these are some of the choices of data structures that we might use to store the open and closed list. What would determine, like what determines what you are going to use? Maybe you guys could throw in the chat, why would you choose an array over a list, over a dictionary, over a queue, over a stack, over whatever? What sort of things would you, you know, like take into consideration when you're choosing different data structures? You would typically choose how you need to access elements, you know, and you're talking about like the efficiency of accessing elements, you know, how fast. And like the efficiency of access, we'll just say. So the question then we ask ourselves is like, how do I need to look up nodes on the open list? How do I need to look up nodes on the closed list? And I think I'm just going to leave it at that for today, because I think this is something that we probably discuss a little bit in tomorrow's class, you know, because it's quite an interesting topic and there is a very cool solution to this, right? So everybody, I'm going to finish at that for today. Big learning outcomes for today were like basically the A-star, graph traversal, what graphs are, how A-star can be used to calculate the lowest cost graph, what does it mean to do lowest cost, and the main features of A-star, which are basically the open and closed list, the heuristic, and that edge relaxation thingy. So that's it, you guys. See you tomorrow. Have a great day.